Okay, 2 o'clock, so I think we should get started. My name's Heather Benway, and I want to welcome you to the OCB 2020 virtual webinar series. OCB is a US-based but worldwide network of scientists working across disciplines to better understand the ocean's role in the global carbon cycle and how marine ecosystems function and respond to environmental change. We're really sitting at the nexus of climate, marine life, and biogeochemistry and studying the interactions among those. Next slide, please. To give you a sense of the scientific breadth of icons depict its overarching science areas. You can find more specific research priorities listed on our website on the About page. OCB has a project office that's based at the Woods Hole Oceanographic Institution, and we receive generous support from NSF and NASA. For those who don't know me, my name is Heather Benway. I'm the Executive Officer of OCB. I'd also like to introduce the host of this webinar, May Mahegan, who is the OCB Communications Officer, and Mary Zawoski, who is OCB's Administrative Associate. Today, we're also joined by 2 members of the OCB Scientific Steering Committee who are serving as webinar co-chairs. Matt Long from the National Center for Atmospheric Research, Lee Stock from the NOAA Geophysical Fluid Dynamics Laboratory. Next slide. You a sense of the webinar series. The schedule is available on our website. You can actually link to it right from the front page. Here's a sneak peek of the next upcoming webinar on September 8th. These typical topical themes with 2 speakers per webinar. To broaden access, we make sure all webinars are recorded and we post them on our YouTube channel a few days after the webinar. We share registration links for these webinars at the URL listed above and also via our newsletter and Twitter. We're currently accepting applications for upcoming webinars, so please go to our website or Twitter feed to access the link to apply. We'd love to continue this series and continue the great talks that we've been having throughout the summer. Next slide, please. To engage with the OCB network in so many different ways that are listed here. You can go to our website for the most comprehensive information. We also have a biweekly electronic newsletter called the Ocean Carbon Exchange. You can subscribe to that right from the front page of our website. You can follow us on social media, on Twitter most prominently, and you can use the hashtag OCB webinar to live tweet during the webinars, during these webinars that we have. And you can find us on YouTube, obviously, to find the recordings of the webinar. And if you have any questions, feel free to email us at this email address listed below. Next slide. So for using WebEx, you can access the call-in details if you find that you're having issues with the internet, which I at present. You can access the call-in details from the upper left-hand corner here if you want to use your phone and then watch the video later. On the bottom of the center panel, you will see an audio button. All attendees are muted to minimize background noise. If you click on participant list, you can see the panelists and the host, but not the other attendees. To access the chat, click on the little message icon. It's a speech bubble, and we will actually post references and other helpful information here throughout the webinar, throughout each of the talks. So definitely keep an eye on the chat. If you have questions during the webinar, you can use the Q&A function, which you can access via this. There's a ... that says more options. And if you click on that, you can find the Q&A. So that's what we would like you to use. If you have questions, you can type your question in and we will be answering them. SC chairs who are moderating this webinar will be moderating the Q&A immediately following the talks. Next slide, please. So the theme of today's webinar is modeling and machine learning approaches to study climate, carbon, and the ocean. Today's speakers are Kasia Tokarska from the Swiss Federal Institute of Technology in Zurich and Chris Holder from Johns Hopkins University. I'm going to let SSC member Matt Long introduce our first speaker, Kasia, while we transfer the speaker
Okay, thanks, Heather. So yeah, I'm pleased to introduce Kasia. She's a postdoctoral researcher at ETH Zürich. Her research focuses on exploring carbon-climate interactions and how they change under anthropogenic influence. She's also interested in providing more robust projections of Earth's future climate using climate models and a variety of data analysis tools. Kasia completed a bachelor's degree in physics with a minor in economics. While at the time it seemed like an unusual combination, it proved to be a good fit for the field of climate modeling and analysis. Seeing the melting mountain glaciers on the Canadian West Coast motivated her further to study the causes and impacts of climate change. The primary source of motivation for her work is the quote from Laudato Si by Pope Francis: "What kind of world do we want to leave to those who come after us, to children who are now growing up?" In her free time, Kasia enjoys outdoor activities, especially if they involve hiking and taking pictures of glaciers or other picturesque landscapes. With that, I'll turn it over to Kasia. Kasia, welcome to the OCB Webinar Series.
Thank you so much for the nice introduction. Can you hear me and can you see my slides?
Yes, we can.
Yes, perfect. All right, well, good morning, good afternoon, and good evening, depends when you are. Thanks so much for this opportunity. I'll be talking today about the climate carbon response, specifically focusing on carbon budgets in overshoot scenarios and pointing out the role of the ocean that plays in moderating the Earth's climate. So let's jump in. Since this is an ocean seminar, I thought I'll start with motivating it with our key player. So this is the ocean, which takes up over the 90% of the Earth's energy imbalance, leading to its increase in ocean heat content and therefore ocean warming. And also the ocean takes up about 23% of our annual anthropogenic carbon emissions to the atmosphere. The land and terrestrial biosphere also take up similar percentage every year, and about half of the carbon we emit remains in the atmosphere. So this kind of balance of carbon and heat taken up by the ocean leads to very interesting relationships in the climate system, which we're going to further explore in this talk. And I'd like to emphasize that the Earth system is highly nonlinear. So the interactions between atmosphere and ocean and atmosphere and land are subject to many nonlinear feedbacks, both positive and negative, and quite often the net effect of the feedback is not entirely known because it's subject to atmospheric CO2 concentration and also warming. So just keeping in mind all those nonlinearities, there's this emergent property of the climate system that if you plot global mean temperature as a function of cumulative carbon emissions, you end up with this approximately straight line. And this is the figure from the fifth assessment IPCC report, which I suppose many of you might have seen before. This relationship continues to be approximately linear up to 2,500 petagrams of carbon emitted. And we actually showed in an earlier study that it continues to be linear even up to 5,000 petagrams of carbon. I mean, of course, we don't recommend testing it in the real world conditions. This is really linear at those high levels of carbon emitted, but this kind of shows us that we can use it as the robust relationship for the concept of a carbon budget. So what I mean by a carbon budget in this talk is the total amount of CO2 we can emit to reach a given level of warming, such as 1.5 degrees of the global mean warming. And this is a very useful concept if you think about reaching the Paris Agreement temperature target, 1.5 or 2 degree warming. The carbon budget tells you this finite amount of emissions that can be emitted in total. So the next question that arises is, what if we miss it? What if we overshoot the budget? What if we emit more than we can? And then we remove this additional CO2 from the atmosphere using some kind of negative emission or artificial carbon dioxide removal technologies? Can we reverse climate change? And also, what happens to the state of the carbon sinks and the state of the ocean? Can we go back to the same state as before the overshoot? So this is going to be kind of the main question to be answered in this talk. And our motivation is also the IPCC special report on 1.5 degree. So currently in the year 2020, we're around here, and they showed there are two sets of illustrative scenarios. The blue ones, as you can see, start declining emission rate almost immediately, and the gray one has some small overshoot, meaning that we don't reduce emissions as rapidly, but both scenarios entail quite high amounts of negative emissions after the year 2050. And the IPCC special report quoted the number of about 100 to 1,000 gigatons of CO2 that can be removed within kind of the plausible, feasible range. And this is approximately less than 300 petagrams of carbon. So this is kind of like the maximum amount of negative emissions we can maybe expect to still stay within the plausible emission pathways. So specifically in the study I'm going to talk about today, we designed idealized emission scenarios, and they entail different levels of overshoot. So the gray scenario is going to be always my baseline. This is no overshoot scenario. It just has a decline of emissions and emissions become net zero. And then we have 4 different scenarios that entail different levels of overshoot and different levels of negative emissions. The more blue the color, the higher the overshoot and the higher the negative emissions subsequently. And all scenarios reach net zero emission level by the year 2020. So we have this type of set of scenarios for different temperature targets, and I'm going to show you the main results for the 2-degree target. And as you had seen from this relationship between warming and total amount of carbon emitted, by design, we designed those scenarios such that the cumulative amount of emission in all the scenarios is the same. So they are all supposed to be reaching the 2-degree temperature target by design. So if you take integral of any of the pathways, you would end up with the same area as the gray pathway here, integral. And we're using an intermediate complexity F-system model, the UVic ESM, and it's being run in the emission-driven mode. So we input those emissions into the model and see how the model responds and what's the net atmospheric CO2 concentration determined by the strength of the carbon sinks. I'll give you a brief overview of the model. So it has the components of the atmosphere, ocean, and land, and they are all connected by exchange of energy, carbon, and water. And the land surface scheme includes dynamic vegetation, Trifid model, and the land surface scheme. These are very similar schemes that were used in the more complex models like the HAG model from the UK Centre. The ocean is also very complex. It's 3-dimensional, 19 vertical layers, and it's similar to the GFDL version of the MOM version of the ocean model. It has both organic and inorganic carbon cycle, which are coupled to the marine sediment model. And the reason why this is, and we also have a sea ice model. The reason why this is an intermediate complexity model and not full GCM is because the atmosphere is non-dynamic. So the wind fields are being prescribed and it's based on energy moisture balance. So you don't get internal variability in this model. However, if you're interested in longer timescales, such as annual or longer, and especially if you're interested in non-atmospheric variables, like I wouldn't look at precipitation in this model, but if you look at carbon cycle, it performs very well and almost as good as the CMYC kind of 5 or CMYC 6 models. And the model is also driven externally by different forcings, and we run it in the emission-driven mode. So we input the emission scenarios and then see how the model responds to it. And just in case you need one more kind of proof that the model performs very well, this is a comparison of the different CMYC 6 models, CMYC 5 models for the temperature and land carbon uptake and ocean carbon uptake. And as you can see, especially land carbon uptake in the CMYC 5 models has quite a large spread. And the UVic model was included in this comparison. And I highlighted it here in yellow, and it's right in the middle of this range of the comprehensive models. So with regards to the key variables I'm interested in, which is land, ocean, carbon uptake, and the temperature net response, it basically behaves the same as the comprehensive models. All right, so coming back to our emission scenarios, I'm going to show you the results for the different overshoot levels, and we'll be always comparing them to the baseline scenario, the gray one, which has no negative emissions. So it's my no overshoot scenario. And the 2 questions I'm going to answer is what happens to carbon cycle responses after the overshoot, and what happens to temperature responses after the overshoot. So let's start with the carbon cycle. If we compare the overshoot scenario to the no overshoot scenario, can we get the same state of the carbon cycle after the overshoot, after we apply negative emissions and try to return the temperature level to our desired like 1.5 or 2 degree target? So this is the resulting atmospheric CO2. So we input emissions to the model determines the carbon in the atmosphere, land, and the ocean. And you end up with this type of time series if you look at the global mean. The blue rectangle indicates the phase of the negative emissions. So by the end of the year 2020, we should have the same state in all those carbon reservoirs. Unfortunately, as you can see, there are small differences. So the land in the high overshoot scenarios takes up less carbon than the no overshoot scenario, while the ocean takes up more carbon than the no overshoot scenario after this negative emission phase. So you can see that this is not entirely identical response. And I'm only considering actually those moderate and low levels of overshoot. So as you can see, like if we considered high levels of overshoot, those changes would probably be even more amplified. So another way to presenting the same kind of result is to look at those three carbon reservoirs, atmosphere, land, and ocean. So for the low overshoot scenario, we only overshoot by 70 petagrams of carbon. We got only a little bit more carbon stored in the ocean and carbon loss on land. And then as you go high level of overshoot, the change is the same, but just amplified. So for the high overshoot scenarios, we have very much ocean stores a lot more carbon and land stores a little less carbon than it did compared to the no overshoot pathway. And so it's interesting now to see where the storage of carbon is happening. So again, this is for the three levels of overshoot. On the color map here, green indicates more carbon uptake by land or by the ocean, and brown color indicates carbon loss to the atmosphere, so it's outgassing. And as you can see, the changes are similar but amplified the higher the overshoot level. So if we look at the highest overshoot scenario, there is more carbon being stored in the mid latitudes and in the equatorial region, both in the Atlantic and in the Pacific Ocean. And there's a lot of carbon being lost, especially on land. If we look at the role specifically of the ocean carbon uptake, it's quite interesting. Again, the change is the same mostly for all the scenarios and gets amplified the higher the level of the overshoot. And the ocean takes up more carbon than the no overshoot baseline in kind of the mid layer between 1,000 to 2,000 meters depth, but it loses carbon at the surface. So you can see very interesting features here because there's like a lot of carbon taken up in the deep water formation region, but then the surface of the ocean starts to be outgassing in response to negative emissions, but likely due to high stratification and low mixing, we get all this carbon taken up earlier on and it gets stuck in the mid layer of the ocean and it doesn't easily go up. So as you might expect, the ocean responds on very long time scales. And here I'm only looking at the year 2200, which was the end of my negative emission phase. So you probably might wonder, okay, what happens after that? Because probably it doesn't stay in this state forever. So if we look at the differences on longer timescales beyond the year 2200, we actually run the model until the year 3000. And here, this is the same plot as on the previous slide, but I'm using a different scale because the changes will be, of course, smaller as we go on. So in the year 2200, we have a lot of carbon stored kind of in the mid layer of the ocean and carbon loss at the surface. And then if we go 200 years later, another 200 years later, and then finally in the year 3000, the ocean finally almost equilibrates. And now you can kind of see prevalent, very small loss of carbon in response to this negative emission. So you can see that this delayed response of the ocean response on really long timescales, even this is about 800 years after the negative emission phase was stopped. So we need to be really cautious of the response of the climate system responding on those timescales. So here I'm going to show you, like, if you prefer to see this in terms of kind of time series. So this is the same information summarized, and I'm using the no overshoot scenario as a baseline. So the gray is zero, the change is zero over time because I mean baseline with respect to baseline is zero, and then this shows us how the state of the ocean carbon uptake changes. So the ocean takes up more carbon than the baseline, and then it kind of slowly releases this extra carbon storage, and then the higher level of the overshoot, the longer the change takes. And then if you kind of want to zoom in this phase here and then lead it until the year 3000, you can see that well, it kind of reaches almost zero, and in the high overshoot scenario, it even crosses over. But it takes a really long time for it to kind of go back close to the baseline level that it was before. And I'm showing a lot more lines here because we also have those scenarios for other targets, but they are normalized here. So basically you can compare and see the common features that for higher level of overshoot, this kind of change takes longer. to do, and then we can do the same type of plot for the land and the atmosphere, and similar features are seen. So as a hint, you can see that the temperature returns to the no overshoot baseline a lot quicker, and the change here is very small compared to the changes in carbon cycle, which take much longer. So we could say that after the overshoot, temperature is relatively easily reversible for this level of overshoot, but the carbon sinks respond much slower. We talk about the carbon, but then the other key determinant factor is warming. So maybe let's look also at the surface, global mean and surface warming, and see how does this change before and after overshoot with respect to the no overshoot baseline. So again, this is our scenarios. And in response to the scenarios, the global mean warming basically is almost the same as the baseline scenario with no overshoot right after the year 2200. So you could see that the global mean temperature is largely reversible after this overshoot, and as we expected, because that by design we wanted the scenario to stabilize at or below 2 degrees Celsius in the scenarios. If we look at the regional temperature, though, it looks a little different. Again, for like very low overshoot, there is virtually no difference, and then the high level of overshoot, we get some lingering warming. However, you can see the scale here is very small, so the maximum change is 0.15 degrees Celsius. So those changes are a lot smaller than the ocean carbon. If we look at the ocean temperature, you can kind of see similar pattern as the ocean carbon, and similar thing happens that we get like a lot of heat lock down here in this part of the ocean. So what is happening is the ocean takes up more carbon, but it also takes up more heat. As a result, global mean temperature is largely reversible. But you can see that like this kind of heat storage and carbon storage then has much longer response than the phase of the negative emissions. So given these responses of the climate system to this negative emission scenario, what are the implications for the carbon budgets for reaching the 1.5 and 2 degree temperature targets? So here I'm coming back to, this is like one of my favorite plots from the IPCC report, this emergent relationship between warming and total amount of carbon emitted, and we can now plot it for this particular set of scenarios. So I'm plotting here cumulative emissions and temperature, and I'm going to put them together on the same graph here. And the pre-overshoot phase, so when the emissions are increasing, it's shown at the bottom part of the graph, and then you reach the 2 degree temperature level for the first time. So this is your carbon budget when the emissions are still increasing, and then you overshoot it by this amount, and then you come back, after the overshoot with the aid of negative emissions, and you reach the post-overshoot carbon budget shown by the red star here. So there is a small difference between the pre and post-overshoot budget, but this is in this scenario design actually part of our design, because we kept the non-CO2 forcing for the historical period according to the historical trajectory, and then we set it to a constant value for the future, not to have conflating effect of non-CO2 to CO2 forcing. So the small difference here between the scenarios is because they actually have a total of net non-CO2 effect different, because they reach the 2 degree temperature target at slightly different years, but it's a very small effect. But generally, you could say that the pre and post overshoot budgets are very similar. And I would argue that for those low to moderate levels of overshoot, we could say that there isn't much substantial difference between the pre and post overshoot budget. So we can overshoot the budget a little bit for 2 degrees target and come back to it, and generally the global mean temperature will be almost the same. However, is it generally true for high levels of overshoot too? So in our study, we considered only the overshoot levels up to 300 petagrams of carbon, which is this kind of plausible amount of negative emissions we could potentially implement. But of course, you can consider much more extreme scenarios in which you have a lot more negative emissions implemented to see if this holds for super high levels of overshoot. And this has been done actually in an earlier study, which is also using the UVic model. And here they used the RCP scenarios, and they used the mirrored RCP. So basically, they mirrored the increase in emissions by the decline in emissions. So what is interesting here is this high emission scenario RCP 8.5 and its mirror part over here. And if you look at the same type of plot, so temperature as a function of cumulative carbon emissions, the pre-overshoot carbon budgets are on the lower part of the graph, and then the post-overshoot budgets are on the upper part. And as you can see here, this post-overshoot budget is a lot smaller than the pre-overshoot budget. So for high levels of overshoot, there is consistently smaller post-overshoot budget, which means if we exceed the carbon budget for 1.5 or 2 degree by a lot, then not only we have to remove what we over-emitted, but we also have to remove extra additional carbon in order to go back to the same global mean warming level, which is a little, which is kind of property of the climate system we need to be careful about. So to kind of summarize my conclusions, the carbon budget concept remains valid for scenarios with moderate to low level of overshoot. So the scenarios I showed you at the beginning from the IPCC special report, they are robust. Even if there's a small level of overshoot, the global mean temperature probably would be exactly almost the same before and after overshoot. However, when you consider much higher levels of overshoot, then this pathway independence doesn't really hold anymore. And we also need to keep in mind that those targets are in terms of global mean temperature, but if you consider other dimensions of environmental change, it's not as easily reversible. So we do get this pathway independence of the carbon budgets for low levels of overshoot, but carbon cycle responses differ already even for those levels. And that's because the ocean is taking up more heat and more carbon, and as a result, we get this compensation, and it results in pathway independence of the carbon budgets. But the ocean state is not the same, and it takes a really long time to equilibrate. So just to look at what is the outlook challenge, the future challenges. So basically the results I showed you are based on the paper we had published last year in AGU Earth's Future. So you're welcome to check it, and it's open access. And there is actually a similar study using also the UVic model from my previous group, the group I was previously at, and they are looking specifically at irreversibility of marine change impacts under carbon dioxide removal, and it just got accepted at GRL. And if you're specifically interested in ocean pH or oxygen and some other biogeochemistry that's using slightly different emission pathways, but a similar concept, they explore a lot more this kind of biogeochemical responses for negative emissions. In addition to it, I also highly encourage everyone to look into more negative emission plausibility, because I think we always kind of assume, oh, we can implement negative emissions later, but really how plausible and how likely it is. So there's this nice review paper in Environmental Research Letters that summarizes a lot of the cost potentials and side effects of negative emissions. And also Nature Climate Change just had a paper published yesterday, particularly about the bioenergy with carbon capture and storage. And they also kind of assess it in terms of the amount of negative emissions used in the special report of IPCC on 1.5 degrees. So it's always good to keep the plausibility part in mind, because we can be exploring the Earth system responses to many negative emission scenarios, but if they are completely unlikely, I think then maybe it's good to kind of keep this concept in mind. So thanks so much for your attention, and I'm happy to answer questions.
Thanks, Kasia. That was great. There is one question from Natasha Romano. She says, earlier studies with CMIP5 models, Friedlin-Stein 2016, show that the TCRE relationship with cumulative emissions breaks down after 2,000 petagrams carbon. What was the reason with the discrepancy with the result we see here?
I don't think, so I'm familiar with the study where they do the intercomparison with the 1% CO2 only simulations, but I don't necessarily think it breaks down the relationship. So the paper one of the very first references I think we shared, there's a Nature Climate Change paper we had about climate response to 5 trillion tons of carbon emitted, and we compared CMIP5 models and also the UVic model and some other intermediate complexity F system models, exactly looking for this kind of TCRE, does it continue to be linear? And it does break down for some of the simpler climate models, so the TCRE kind of curves down. And for the complex models, it continues to be straightforward. And the reason for it is that the more complex models have more realistic ocean heat uptake representation. So the ocean, in a way, saturates at some point and takes up less heat. And that's why you kind of get this compensation. While in the more simpler models, some of them have maybe like infinite ocean heat uptake. And if the ocean continues to take up heat while your kind of, like the other effects are not compensating it. So I mean, we use CIMIC 5 models for that and compared with EMIC. So I don't think this breaks down in CIMIC 5 models. And in the CIMIC 6 models, it also continues to be linear. We plotted it for the high ECS models from CIMIC 6, and it continues to be linear. So I don't know exactly what this question is referring to.
Okay. I think in the interest of time, we'll move on. There's a couple more questions. One from Zhanghen's Zhang. Could you please explain what processes are considered in land-ocean interactions?
Oh, land-ocean interactions. Oh, I'm sorry, I can't remember from top of my head, but we shared a link to the paper of the UVec models. You're most welcome to read it. Sorry. Land-ocean, yeah, that's not usually the connection I talk about.
Okay, one final question from Keith Lindsay. Have you looked at stressors of ocean ecosystems in the overshoot scenario experiments that you ran?
No, so I think that's this paper I mentioned, the one in general that just came out. They kind of look more at the like the biogeochemical responses, but we only looked at the physical, like the ocean carbon uptake and ocean heat uptake in this particular study.
Okay, so I think in the interest of time, we're gonna have to move on, and I'm gonna turn it over to Charlie Stock from GFDL to introduce our next speaker, Mr. Holder. Thanks, Kasia. It's a great talk.
Thanks. I hope everyone can hear me okay. It's my pleasure to introduce Christopher Holder, who's a PhD candidate at Johns Hopkins University, the Department of Earth and Planetary Science, where he works with Dr. Anand Nanadesikan. His research focuses on using machine learning techniques to better understand phytoplankton in Earth system models and in natural observations. He has a number of hobbies, including drawing, skiing, hiking, and other outdoor activities. When he finds a new passion, he tends to go all in. One such example is over the course of the last few months, he has learned how to fix numerous things around his apartment, which has led to a newfound curiosity for taking things apart and putting them back together again. The most recent appliance where his curiosity was applied was his wife's old laptop, which is now in great condition. So I guess you could say Chris has an interest in both machine learning and learning about machines. So with that terrible joke, which is all my responsibility, I will pass it to Chris and let him tell you about his work. Thank you.
Yep. Thanks, Charlie. Trying to share screen. One second while I get set up here. All right, can you guys see the slides and hear me okay? Yep, okay. So thank you, Charlie, for that introduction. So basically today I'm just going to be talking to you guys about machine learning and some of its potential uses in oceanography, exactly as the title describes. So I just want to start with kind of how I got started with machine learning. This really all kind of started when I was in my advisor's biogeochemistry class, and we were looking at plots such as these, where what you can see is on top here, you've got things like chlorophyll, and then we were trying to compare things like nitrate, phosphate, and light to these things. And my question had been, isn't there an easy way where we can basically just take all of this information and kind of feed it into a computer? And in my head, it was really easy that there's got to be techniques out there for this, but of course it's not quite that easy. So I approached my advisor and basically asked, do you have some data that I can play around with? And we thought about maybe using machine learning for this. And so he gave me kind of a toy data set, just output from one of his simpler Earth system models. And so we were essentially trying to predict the biomass variable for phytoplankton using things like nutrients and light as predictors. So I played around with it for a couple of days and gave very surprising results. It was something similar to what you're seeing here. So in the top is the true response to the model, and on the bottom is just the machine learning algorithm's predictions. And so what was interesting to us is that it gave such a good response. And so obviously we're scratching our heads and we're like, okay, we've got to be doing something wrong because there's no way you can give predictions that close to what they were. And so basically we sat down one afternoon in his office, talked for a couple hours, and that's when we kind of found out that actually we were doing everything right. The machine learning was doing pretty well. And so he became a lot more excited in it after that. And so did I. And so that's when we started looking at other sorts of methods as well. So on the top right is just multiple linear regression. You can see that one doesn't do as well. And then in the bottom right is just neural network prediction. So you can see that the machine learning algorithms do pretty well. And so after we started to play around with this and see the kind of things that it could tell us, we got really excited about this. And we started thinking about all these possibilities and things that we could apply it to. And so that's kind of how I got my start with using machine learning in oceanography. It really just kind of developed as a side project, and then it ended up turning into the focus of my dissertation. So we've really had to work on the terminology with how we're trying to characterize these things, and we found that things generally fall in two camps when it comes to phytoplankton. So you've got things like intrinsic relationships, where you're talking about things like small scale relationships, things like laboratory experiments. So an example would be like nutrient growth experiments, where you can change one thing and then see how that variable responds. See how the phytoplankton respond to that one variable. And then in contrast to that, you've got apparent relationships, which are like those really large scale relationships. So things like ecosystem level. So an example of this would be like looking at satellite observations and like distributions of nutrients and trying to compare them. And the big difference there is that in apparent relationships, you can't vary one variable at a time. You're looking at the relationships of the intrinsic relationships and seeing how they turn out. And so one thing that's really important to note here is that a lot of our observational data sets are looking at things like apparent relationships. So they're looking at how all of these intrinsic relationships interact. And so I can demonstrate this a little more clearly with an example. So one of the questions that we've been trying to answer is, how do you relate intrinsic and apparent relationships in these different scenarios? So an example of this is, so this is an example of an intrinsic relationship. So if you're familiar with Michaelis-Menten dynamics, the basic principle is that increases in a nutrient concentration have diminishing returns in growth rate. So on the x-axis is just an arbitrary nutrient, so things like phosphate concentration. Then on the y-axis, you've got phytoplankton growth rate. And so you see, as you increase the nutrient concentration, you're getting diminishing returns on that growth rate. And so if we kind of imagine a simple scenario where we've got two of these things, so on the left, we've got light concentration, and on the right, just an arbitrary nutrient concentration. And then we'll put those in the corners. So then if you think about how these are distributed across latitudes, so that's what you're seeing in the bottom plot. What we did for this simple example is just, we said nutrient is increasing towards the pole and light is decreasing toward the pole. So when we look at these, we can say the low nutrient areas are nutrient limited and the low light areas are light limited. And so when you see patterns like this, you might get growth rates that look similar to this green line here, where basically when both are less limiting, you get these higher growth rates. And so that kind of leads me to where I point out what intrinsic and apparent relationships are. So by the definitions that we've kind of defined them, the intrinsic relationships are those two nutrient Michaelis-Menten dynamic curves. And then how they interact in the environment is what you would see from things like the green line. And so that's kind of two of the big important terms that we've had to kind of wrangle in learning all this. But briefly, I just also want to explain what machine learning is to me, kind of in my head. So it's in the simplest terms, it's basically just making small adjustments to weights and biases for a model. So you've got observations, you've got predictions, and then you've got some algorithm that adjusts itself so that the error between those observations and predictions is less. So if you take, for example, like this Kirby plot here with a bunch of observations, if we try to fit a linear line to this, you can see that it tries to fit, sorry. Maybe these work, maybe they won't. There it goes. So if we try and fit a linear line to this, basically it's adjusting itself, and then it kind of hones in on a good fit for it. But obviously this is nonlinear data set, so you need a nonlinear method. So if we use like a machine learning method that can fit a nonlinear relationship, we can get stuff like this. And then if we think about this in 2 dimensions, essentially what you're seeing on the left is a function that we're trying to fit, and on the right is just a neural network fitting itself to that function. And if you get nothing else from this slide, it's just fun to watch. So that's kind of what machine learning is to me. And 2 of the main methods that we've mostly used are called random forests and neural networks. And so I'll try and give you a 30-second spiel on each and what they are briefly. So random forests are just a collection of decision trees. And so what you're seeing on this slide is a single decision tree, where basically what it does is it takes the entire data set, and then based on some value of one of the predictors, it splits it so that basically the error is minimized between those 2, and then it splits it again and again and again, and you get these trees that are basically just a lot of splits of the original data set. And so this single decision tree is what you can think of as a single tree, and then a random forest is basically just kind of a collection of these trees. And so by averaging the predictions over all of these trees, you get a prediction from the random forest. And then neural networks, they're a little harder to explain. The best way I can explain it is if you think about linear regression, where there's weights and biases, but in this case, it's just there's a lot more weights and a lot more biases that have to be adjusted. And so the typical layout of a neural network is you've got your input layer, which is basically just your predictors. So each circle there is one of your predictors. You've got a hidden layer where basically you're forming connections between each of those. And then you've got your output layer, which is where it gives you that final prediction. And so within each of these hidden layers, you've got some sort of function that's being fit to each of those. Now, the thing about machine learning that a lot of people are, and the reason that people are hesitant to take it up is because there's this idea that there are these black boxes, in the sense that you give input to a machine learning algorithm, it does something, and then it gives you a result. And that's a valid point in a lot of ways. And so what we've been trying to do is look at ways that we can kind of make it not a black box, where we can actually learn something from that data set. We can know what it's doing, what relationships it's finding in the data in order to get that output. And honestly, the simplest way that we've done that is just a sensitivity analysis. So if you think about this, where you've got 3 variables, you've got one variable going from its minimum to its maximum, and then you're holding 2 other variables at their average values. You then give that to your machine learning black box, and then it spits out what the relationship is. And then you can also change one of the values of those other 2 variables and see how the line responds. And so if we think about this as an example, I like to think about mental focus during conferences. So what you're seeing here is kind of the ideal scenario, where basically, in the middle of the day is when your focus is highest at a conference, and then it starts to come down a little later, and it's dependent on things like how much coffee you've had, your sleep quality. Well, if you decide to have less coffee one day, you can see that your mental focus actually goes down through the day. And so that's just a simple illustration of sensitivity analyses. And so now I can finally get to the research. So some of the examples that I'm going to be covering today, and some of the ways that we've thought we can use machine learning is, number one, an Earth system model output, looking at how different phytoplankton groups respond in Earth system models, and then also looking at variable importances and their interactions in an observational data set. So on this very first one, basically what we did is we used a monthly averaged output from a simplified Earth system model. And what we did is we gave the machine learning algorithm, in this case, we were using multiple linear regression, random forests, and neural network ensembles. We gave each of them 3 predictor variables and 1 response. And so basically we were asking them to take a macronutrient, micronutrient, and light, and try and predict biomass. And so this is what we get. The black circles that you're seeing are just the observations. And I know there's a lot to see here, but I'll break it down for you and try and draw your attention to the important points. So in the columns here, we've got the macronutrient, the micronutrient, and the light. And then on the rows, we've just got the percentile values in the sense that that's what the other two variables are set at while that one particular variable varies. And then what we're seeing here is that, or rather the result that I wanted to highlight is more the green lines. So the green lines are the neural networks, and those are the ones that we found can give us the best responses in terms of the relationships that we're looking at. But we wanted to kind of point out that, you know, the biomass only shows significant gains when the micronutrient is not limiting. So this middle one here. Whereas on these other two, we don't see quite as many gains when the others are less limiting. And so what we found from that is just that, you know, it helps find apparent relationships between predictors and response in our system models. But then the next example that I want to talk about is we were wondering if, you know, if we have in our system model and we've got two groups of phytoplankton, so we've got small phytoplankton and large phytoplankton, can we use the machine learning to kind of tell how each group responds to the same conditions? So what we did is we used neural network ensembles, similar to what we did before. We had 3 predictor values and 1 response. And so there was a neural network ensemble trained on each of the phytoplankton groups. And so this is what we get. So we get phosphate in the top left, iron in the top right, and then irradiance in the bottom. And the thing that I want to draw your attention to is that iron seems to be the thing in which they differ the most. So it seems that large phytoplankton are much more sensitive to iron concentrations. And so I also wanted to look at this in terms of two-dimensional responses. So on the left, you're seeing small phytoplankton, and on the right, you're seeing large phytoplankton. So in this first case, you're seeing the interaction between iron and light. You can see that as iron increases, light the phytoplankton can get more biomass in the large group. Same thing if we look at iron and phosphate, but then when we take iron out of the equation, small and large phytoplankton react pretty much the same. And I also wanted to verify this in the observations in some way to visualize. And so what you can see here is these are just scatter plots with phosphate, light, and iron. And the thing I'm drawing your attention to is the one on the right. You can see that there's higher biomass values with increasing iron compared to the one on the left with small phytoplankton. So that brings me to my second point in that, you know, it can help us differentiate how phytoplankton groups in the same Earth system model respond to similar conditions. And so for this last example, I just wanted to point out how we used it for an observational data set. So in this particular case, we used a data set from the Chesapeake that covered about 10 years with sampling the same locations every 2 weeks. This is part of a monitoring program between the state of Maryland and the state of Virginia, multiple universities involved, different state agencies. They have a great, very rich data set available online, and that's where we were getting a lot of our data. So the variables that we included were things like nutrients, phosphorus, nitrate, ammonium, physical variables like temperature and salinity, and then geographic variables like longitude and latitude. And so in this particular case, we were using random forests since they're known for being able to find variable importance metrics, so being able to tell you which variables are most important in a particular data set. And then we also wanted to know if it can tell us anything about the interactions between these variables. And so the question that we were trying to answer is which of these variables and interactions most affects the concentration of dissolved oxygen in the Chesapeake Bay. And so briefly, I just want to say that when I'm talking about a variable interaction, so a first order interaction is how one variable affects the outcome. Second order interaction is how two variables together affect the outcome, and then likewise for third order interactions, and you can continue on for higher order interactions. But generally, the way that we try to simulate that in our data sets is you basically just multiply one variable times another for second order, and then you multiply a third, and you can continue to do that for higher order interactions, but obviously the more interactions you have, the more variables you have, and the more variance you have in the data set. So we stopped at third order interactions. And so we wanted to know, can we use random forest to determine which variables are most affecting dissolved oxygen? So this is the result that we get. So on the x-axis, you're seeing the interaction between the latitude, the salinity, and temperature. On the y-axis, you're seeing the dissolved oxygen. And it seems to us that there was two camps that most of the data seems to fall into. So the higher oxygen concentrations would be things like at the surface during the winter and things like that. But we were curious about the low dissolved oxygen, and so we decided to do another, ask another question where basically we're asking what variables are most important for dissolved oxygens below 2 milligrams per liter, which would be considered hypoxic. And what we found there is that the interaction between ammonium, orthophosphate, and total phosphorus was most important. And like I did in the second example, I obviously like to confirm this by visualizing it myself. So what you're seeing here is the ammonium on the x-axis, orthophosphate on the y, and on the z-axis, you're seeing total phosphorus, and then the color corresponds to the oxygen concentration. And what we're seeing is that at these lower concentrations of orthophosphate, ammonium, and total phosphorus, you're seeing these higher oxygen concentrations. And so that leads us to the fact that it can help us locate important variables and some of their interactions in observational data sets. And so these are our main conclusions from some of the projects that we've done, where basically we found relationships in our system model output. We were able to see how they tell different phytoplankton groups apart, and then also looking at important variables and interactions in observational data sets. But something to note here is that some of the limitations of the projects that we've done is that they aren't accounting for things like time lag or other lag effects that may be present in the environment. So it was like the points where nitrate was measured, that's also where dissolved oxygen was measured. So it wasn't considering those upstream, downstream effects or any effects that time may have. So that's something we may try to account for in the future. And I just want to acknowledge some of my co-authors and co-scientists. So Anand Ganana-Deskin is my advisor, and then these are some of the other scientists that we've been working with at Johns Hopkins. And of course, family and friends, National Science Foundation, and my university and department. And with that, I'd be happy to take any questions. Yeah, thank you.
Thanks very much, Chris. Great talk. Do you have any questions coming over the Q&A? If not, I will send one myself. See if that goes. Except that I can't send it. So I do have one.
Yeah.
I'll apologize. I'll need to send this to you afterwards for the record here. But your talk got me curious as to whether there might be machine learning derived relationships and sensitivities from observations that might serve as emergent constraints on ESMs to help constrain projected changes. Do you see any potential for that based on your work thus far?
Yeah, absolutely. So what you're asking is, can we find relationships in the observational data sets that we could then apply to the Earth system models? Is that?
Well, yeah, so then you could presumably assess whether the Earth system model is showing the same emergent relationships, right, and potentially constrain whether or not they're responding in a consistent way to the environmental forcing or not, as a way to potentially refine future projections.
Yeah, that is something that my advisor approached me about, and I certainly think it is possible. Unfortunately, I'm working on so many projects as is, I haven't been able to undertake that. But yeah, so one could certainly do that. So basically taking the observational data sets, looking at the apparent relationships that they get, kind of altering the conditions to see what those relationships are, and then comparing them to Earth system model output. So if you're looking at like observational data sets that are monthly averaged, and then looking at Earth system models, which are monthly averaged, you could probably make a comparison between the two to see if the apparent relationships kind of match up, and see if those Earth system models are getting the right relationships.
Great, thank you. And we have another question that has come in. Adam Kimberling asks, hi Chris, have you spent much thought on how to address temporal lags or seasonal periodicity in predictors and the phytoplankton responses that you are modeling?
Yeah, so the time lag issue is one thing that we're really trying to understand, and I think the thing that would be able to help with that is knowing variables like the currents, so like how fast water is moving up or down through those points. So if you know that the currents are moving at some speed, you can then maybe take the concentrations from so far upstream and apply those to the point that's being measured at that time. But yeah, we have tried to give it some thought, but there's a lot of challenges right now. And we're always open to suggestions on anything that anyone has. But right now, what we've been trying to do is take into account physical variables, things like circulation, currents, wind, so things that could affect or tell us, give us some information about how fast things are moving.
Okay. Are there any further questions for Chris? All right. Well, thank you again, Christopher, for your talk today. And I guess that concludes the two talks. So maybe I'll turn it back over to May or Heather to give us another preview for the next one in our series.
Yeah. Thank you, Charlie.
Yeah. Thank you again.
Thank you. Thank you, everyone. And thank you especially to our speakers for two great talks. Again, we'll be back on September 8th. We hope you'll join us. We'll be advertising changes in the ocean's organic carbon cycle. It will be the next webinar theme on September 8th. And again, if you're interested in applying to speak in the webinar series, please follow this link or just go to the front page of our website and you'll be able to find it there. Thank you, everybody. Have a great rest of your day.